The Hong Kong Polytechnic University, PolyU, leverages its world-class academic and research excellence to develop innovative solutions for a more sustainable tomorrow. In July 2022, the PolyU Academy for Interdisciplinary Research PAIR was established as the university's central research platform, dedicated to providing world-leading interdisciplinary solutions to address significant societal challenges. PAIR is composed of multiple constituent research institutes and research centers. Each research unit focuses on a particular research area and is joined by researchers from various PolyU faculties, schools, and departments. PAIR research areas include advanced technologies and manufacturing, good health and well-being, and smart and sustainable cities. PAIR researchers develop new materials, systems, technologies, and techniques that support industrial modernization, upgrading, and transformation, look into the factors and mechanisms influencing human health and wellness, and develop evidence-based solutions, and generate smart technology-based solutions for making urban operations and services more efficient, connected, and eco-friendly. We particularly value impactful collaborative activities in research and scholarship. PAIR researchers pursue research collaboration at different levels. In addition to interdisciplinary collaborations within and between research units, PAIR and its units establish partnerships with industries, governmental bodies, universities, and other external stakeholders. With internal and external collaborations, we have successfully translated PAIR-led innovations into commercializable solutions and practical applications, and established joint laboratories and research entities with external organizations, driving scientific breakthroughs, innovation, and technology development, and socioeconomic prosperity. PAIR's research excellence and research impact have been widely recognized at local, regional, and international levels. Our research outcomes have been published in leading journals, including Nature and Science. Innovations led by PAIR researchers have won prizes at various competitions and events, including the International Exhibition of Inventions, Geneva. Many PAIR researchers have been named among the world's top 2% most cited scientists in their own areas of specialty. Individual researchers have been selected to the National Academies of Science or Engineering and as fellows of professional associations, and have been bestowed with local, national, and international awards and honors. Harnessing the strengths of PolyU's research and world-class scholars, PAIR will continue our unwavering efforts in research and scholarship, knowledge transfer, and collaboration to develop impactful solutions that benefit Hong Kong, the nation, and the world.
Dear Professor Driscoll and Professor May, Professor Su, and professors and colleagues, and good afternoon. We are gathering today to listen to Professors Judith Driscoll of Cambridge University to deliver PAIR Distinguished Lecture. On behalf of Professor Chen Xingyan and PAIR's Director, I warmly welcome you and our speakers together and wish everybody an enjoyable afternoon. And now Professor May Yu-Wing, and PolyU Distinguished Chair Professor in Composite Science and Engineering, will introduce our distinguished speaker, Professor May.
Thank you very much, Professor Tao. Ladies and gentlemen, it is my great privilege to introduce our distinguished speaker today, Professor Judith Driscoll from Cambridge. Professor Driscoll is a world-leading material scientist, and in today's AI era, there is a growing demand for computing power, and that really creates an urgent need for more energy-efficient technologies. Professor Driscoll's research is helping to meet this challenge by leveraging the power of functional oxides. And functional oxides are a particularly promising class of materials since their properties can be tailored for applications which range from advanced computing as well as clean energy technologies. And Professor Driscoll's research group at Cambridge develops energy-efficient oxide materials for ICT and energy devices. And allow me, ladies and gentlemen, just to cite a few examples of the great research impact of Judith's work. First, in computing, as the Royal Academy of Engineering Chair in Emerging Technologies, she leads a 10-year project to develop scalable, non-volatile, resistive memory devices. And this technology stores data not by electrical charge, but rather through changes in the thin film resistance. And second, in clean energy, a group's research has demonstrated the potential of engineered oxide materials for efficient water splitting to produce a green hydrogen. So together, these innovations are helping to shape a more sustainable future for both computing as well as clean energy. Professor Driscoll's scientific excellence has been recognized through elections to the Royal Society and the UK's Royal Academy of Engineering. More importantly, is beyond her research, she is really a dedicated mentor and advocate for women in science and supporting and inspiring researchers across all their stage careers. So that is, to me, a really great achievement in itself. So without further ado, ladies and gentlemen, I would like to invite Professor Driscoll to come forward and deliver her lecture. So let's welcome her in the usual way.
Well, thank you very much for that really wonderful introduction. I feel very honoured and humbled by those very kind words. So it's also a wonderful pleasure to be in Hong Kong. It's my first time here, amazingly, and it's a really inspiring place. And the food is absolutely amazing, actually. So thank you for having me here. So I'd like to try to tell you some broad things about some of the work I'm doing, really in the materials engineering of thin films, particularly oxides, to try to meet the performance requirements for electronic applications of these materials, because they're quite complex materials, more complex than people really understand, I believe, anyway. Professor Wing mentioned some applications of oxides, and actually there are very, very many, because they span all the way from insulating, dielectrics, very, very insulating, to highly conducting in the form of superconductors. So they have interesting properties because of their interesting structures and their ability to be tuned easily. So we can think of areas such as energy area, such as fuel cells, catalysts, photovoltaic materials, optical, tonic systems, magnetic materials for ferromagnetic materials, multiferroics, and electronic, so superconducting, ferroelectric, semiconducting, spintronic. And really, I've worked in many of these areas. I'll focus today on the semiconducting aspect. And the key thing I do that's sort of perhaps different to many others is to think about how to actually make the materials, understand the science, and then fabricate them in thin film form so that you can get the performance you want. Because getting the performance is actually quite hard. Now, a lot of people in this field focus on really complex materials, often perovskites or spinels or double perovskites with ternary compositions, because it's here that you have the most interesting functionalities. So I've just put up a few examples there where you see there's many, many complex structures, and the properties are things like multiferroics, as I mentioned before, photocatalytic, or even polar topologies. So really fascinating physics all the way from quantum to semiconducting, and everything, sort of all these interesting properties that you can get. Now, the problem with all these things is that, and all these materials here, is that they're really impossible to turn into applications, in my opinion, let's say. Maybe nearly impossible is a little bit of an exaggeration, but it's very difficult. And there are not many applications of these materials in thin films today, despite the decades of research and the decades of wonderful discoveries. So that's the thing I'm trying to overcome, is to think about what we need to do to make them have the performance they want. So this is the question I want to ask you, and we're trying to answer today, is can we achieve widespread electronic technologies from oxide films? Perhaps some of you here are working on oxide films in some form or other, but can we really get these technologies is the question. So, as you know, material science and engineering kind of links the physical sciences to the engineering applications. So to get engineering success and to go from the pure sciences, you've got to link these things. And this is where material science and engineering comes in. A lot of our work over many, many years has been looking at a range of materials with different properties. I've mentioned some of the properties already, but the core thing is saying, what can you do with those materials? What can you do with these basic devices to make them really work? And a lot of our work is to try to understand, to improve, to license that, to create patents and to try to license that technology, or simply to collaborate with industry on these areas. So just some examples of companies we've connected with over many years. Some of it's been licensed, some of it's collaboration, but a lot of interesting things and collaborations. And as I said, it's about the engineering is the bit that's missing, I would say. If you think about being at this conference with all the structural materials people, they spend a lot of time engineering the materials to get their properties right. This field, it's not so much about that, it's more about the science. And I think the engineering bit is the bit that's missing, and that's the bit that I'm really interested in. So I'm going to focus on the area of memory today, and memory in a broad sense being non-volatile memory for either memory applications or for new forms of computation. So you can put non-volatile memory materials in adapting that for in-memory computing, so like neuromorphic brain-like computing. So that's the thing I want to talk about today. We all know about the numbers of data centers, the huge numbers of increasing numbers of data centers. We know about the AI applications that are all over the place today. So this could be in satellite technology, it could be in medicine, it can be in transportation, many different areas where AI is crucial and is being adopted very rapidly. So as I said, there's many memory technologies. I won't talk about all of them. I'm going to focus today a little bit on edge computing. This is using in-memory computing for edge AI. And here, the benefits of trying to use a neuromorphic style technology, as I show up here. So showing this over here. If you use a crossbar array of memristor structures, showing here, this large crossbar array, this array can mimic how the brain operates. You can have synaptic connections between the crossbars, and the neurons are being like the bars themselves. So you have both synapses and neurons in this array. So the question is, for this in-memory computing structure, what materials would you put in there, and how do you control them? The benefit of this for edge AI is that you minimize latency and real-time processing, you reduce the power budget, and you reduce network congestion. You're not going to be so dependent on the cloud. Very important today in transportation, in IoT devices, in your homes and in your societies, in all sorts of military technologies, of course. So there's importance of new kinds of computing where CMOS is hugely inefficient. And that's using this crossbar array structures with interesting materials. So this edge computing market is growing very rapidly. So between 2026 and 2031, it's predicted to grow by 23%. It's a very large market, nearly $1 trillion, maybe over $1 trillion in 2031, well over $1 trillion. But this is the area we're going to think about today. So as we heard at the introduction, AI is using huge amounts of energy. The amount of compute is doubling every 2 to 3 months, and it's really unsustainable. And of course, that goes along with cost as well. The cost is humongous. And again, it's exponentially increasing. As we see here, it's millions and millions of dollars. And really, one would think, are we going to come to a roadblock here? How are we going to overcome these problems? Just to consider that training a single large natural language processing model can consume as much energy as a car of its entire lifetime, including the energy to build it. Now, our structures and devices are not necessarily going to replace the training part, but it's going to be more at the edge of the inference part. This is taking the models and then applying them and using them. But still a lot of energy to be saved and all the other advantages of speed and security. Here we are, the human brain. What we're going to try to make is this like synapse here, which only uses 20 watts of total power. The brain is 1 million times more energy efficient than CMOS computing. It's hugely more efficient. So all these chemical processes in our brain or biochemical processes, I should say, are hugely efficient. Silicon CMOS-based electronics is not efficient because you're moving electrons around between the memory and compute many, many times, especially during the training. And it's not a very energy efficient process. So we can think about many different types of non-volatile memory technologies. In fact, there's many out there that are being studied. But I'm just going to focus on 2 today, and that is resistive RAM and ferroelectric. So resistive memristors, so materials that change their resistance and remember their resistance over time, and the same for ferroelectric. So you can call that RAM, or you can just call it memristors based on resistive. Different technologies, different wording can apply, but let's just think about what we're going to do here. So these materials hold strong promise for edge AI. And the computing power compared to your SRAM in your computers is much lower. MRAM, magnetic RAM, is a widely used technology, but it has some higher computing power, but also it has some issues in terms of this edge AI area that we're interested in terms of what kinds of memory levels you can get and how small you can make the devices and other issues. But the resistive and ferroelectric are of great promise. But those technologies are not new at all. They've been around for a very long time, so decades, in fact. And yet we still don't have widespread applications of these in non-volatile memory. There are some, but these are not widespread, and they're certainly not widely spread in edge AI. There's many startups, but it's not quite getting them. The materials have challenges. So what are the requirements for advanced memory? And you see here, we list a number here of different requirements that you have to fulfill. There's many. You can't just go for one, you can't go for two. You really must fulfill different combinations of these. Depending on the memory, particular memory technology, they have different requirements of these. But the challenge for resistive memory, mainly endurance, voltage current levels, retention, stochasticity. And if you look here, this is the resistive technology, and this is showing that actually, how does it work in oxide resistive materials, which is the most common type and the most cost-effective, let's say. You have the formation of a filament based on oxygen vacancies. And the top of this filament can be basically switched on and off with a field. So you move the vacancies either forming a complete filament, or you move them away and then you form a cut-off filament. And that gives you high and low resistance states. So it's basically forming these defect channels. They're very random though, and that is a problem. The randomness, sometimes the size of them, and when you have a full filament going all the way through that's quite large, that can give you a very low resistance, and that means huge energy use. We don't want that. We want to be able to control those filaments, control these structures. For the ferroelectric materials, we have similar requirements, and of course, we have different challenges. So endurance, switching voltages, you're able to get different multi-level states, because I'm going to talk about analog sort of memory, so not digital now, but many multi-level states. That allows us to have our crossbar working very effectively, because the crossbar with our materials in between, what you do is you have vector matrix multiplication by having different currents passing through those cross points through the device, and you sum up the currents using Kirchhoff's law. It's a more simplistic, in a way of doing the computation, rather complicated, because you can tune the current by tuning the resistance levels in the materials in between in the crossbars. So that's this multi-level analog memory part. You change the resistance of the material with the voltage, and so it's that analog different conductance states that you want to get. So this is a bit harder, you know, in the ferroelectrics compared to resistive. So it's balancing them. It depends on the materials, it depends on the whole structure, but overall you need to be able to improve some of these things, and things like scaling as well. You need to make them very small and energy efficient. So this is how the ferroelectric one works. You basically can just polarize it up or down. You have a charge, either positive at the bottom or positive at the top. And that's non-volatile, because when you remove the voltage, that current is, the polarization state remains. And the current through the device is just how the polarization changes with time. So these are non-volatile materials. So are the resistive, non-volatile. As I said, all of these things that we're looking at are non-volatile. It means that when you remove the voltage, the state remains, whatever that current state is. And here, how you would say, well, how do you move oxygen vacancies through a thin film at room temperature? They're not very mobile. They have a large activation barrier. Well, that happens by reducing the activation barrier here. So the current is proportional to the activation barrier minus this field that you apply. So if you have a large field across your film, then you can reduce that barrier. And as you see here, 1 volt across a 10 nanometer film is around 1 megavolt per centimeter. It's quite a large field. And the films are all that around that thickness. So you have this field-induced barrier tilting, and you can lower that migration barrier and cause these ions to move with the voltage. So that's the two basic simplistic technologies, but the materials are challenging, so that's what we'll talk about. So the challenge is high endurance. That means many, many times that switch it. High retention, that means you must retain the state over many, many decades of seconds, 10 to the 8 or more. The switching voltage and current may be too high. You want to have small voltages to switching it. You want line around a volt. And the current must be low. 100 microamps is sort of a ballpark figure to keep, let's have that low current. Non-uniformity, when you switch it many times, you want the loops to go overlapping each other again and again and again. You don't want variations in the loops. Can't have non-uniformity. You don't have non-uniformity in your CMOS circuits, so you mustn't have this here. And you must have these multi-level states. So when you have your crossbar array, you can have different resistance levels. You can have different currents through there so that you have analog computing. And so getting these resistance levels to be uniform and separable, separated from each other and not overlap, is a materials challenge as well. If you look at the solutions to all these problems, a lot of them relate to control of oxygen vacancies and the motion of these vacancies through the film. So you're controlling their concentrations and controlling their motion in the material. So how do you do that is the question. Now let's look at the ferroelectric ones as well. Same kinds of problems. Very interesting ferroelectrics are hafnia and zirconia in recent years. These have been studied very widely. And here, again, we have oxygen vacancies in these materials. So you just lose some oxygen atoms that come out, leave these vacancies. And the switching occurs by some slight tweaking of the structure when you apply the voltage across it, and you see the polarization moves up and down as you change that structure. But as you see in this right-hand graph here, if you look at the formation energy of different structures, rhombohedral, tetragonal, thrombic, monoclinic, they have very similar formation energies relating to the vacancy concentration. So for a vacancy concentration of 1 atomic percent, you can see that the formation energy, all these structures, is about the same. So you might be able to fix on the structure in the first place, but once you start applying a voltage and cycling that and switching it, and you're moving it many times and you're moving the oxygen around, you can change the oxygen content a little bit, and then you're going to change the phase. Then you might not have a ferroelectric phase because only polar rhombohedral, the polar phases of rhombohedral and orthorhombic. So if you start forming monoclinic or tetragonal after cycling and losing some oxygen, it's not going to be ferroelectric anymore. And then the thing doesn't work. And so that happens a lot. This cycling, as you cycle it, the oxygen does move and you do see that things degrade. So the question is how to control the material to keep the oxygen in, to control the phase you want. So again, the challenges are similar. On the left-hand side, we see all the problems, well, the requirements, endurance, retention, switching voltage, slightly different things here. We've also got imprint and wake-up effect. Imprint is how the ferroelectric loop becomes shifted. If you move some vacancies and they get trapped at one of the electrodes, that can cause the loop to be shifted. And there's also the wake-up effect. Often these ferroelectrics don't work at the start. You have to apply voltage to wake it up. You have to change the oxygen, move the oxygen around before it becomes ferroelectric. So all these things are there, and many of them relate to these control of the vacancies and control of the concentration. So that's where we're at. That's what we need to do, is to think about all these problems and try to solve them. So if we think about what a thin film looks like in a cross-section, on the left here, we see that we have a film. It could, ideally, you'd want a single crystal, but oxides have very high melting points, and it's very hard to make a single crystal in a practical way. If you think about a CMOS foundry, you want to do things at lower temperatures, you want to save energy, and so the way to do that is to make a polycrystalline material at lower temperatures, or even an amorphous one. So I show some structure here in a polycrystalline material, but actually amorphous materials also have structure. Some of them are semi-crystalline. They're not always a perfect uniform thing. And so you have problems in how the oxygen can move through here, because the oxygen vacancies can get pinned at defects, or they have tortuous paths. They can get stuck at the interface, or they can grain boundary junctions. So all these different defects can alter the path or block the path of the vacancies, and we don't want that. So if you look at the interface here, that's people don't really look much of thinking about this interface. That's something we are going to talk about a little bit later. We must control the interface as well. So ideally, you don't want those hands there, red hands, you want yellow arrows. You want the vacancies to move up and down. You want it to be a beautiful structure where you control this. And so you want a nano-engineered electrode, a nano-engineered interface, and a nano-engineered switching layer. And so you need to control the vacancies in the film. You need to have facile motion in the switching film, in the electrode film, and at the interface. Note I'm only showing one electrode. Of course, you'd have to have two electrodes, but we don't need to deal with both, right? Just show one. And so what my group does a lot of is thinking about this thin film design, defect control, select the right materials combinations, and nano-engineer the interfaces so that you can actually get this beautiful, perfect structure on the right that you want. We've done a lot of work in this area, applied to many different functionalities. And here we're just applying it to this memory technology. So here we go. This talk, we're going to control the vacancies. We're going to have easy motion. How do we do that? If you look at the top image here, there's three images here. This is if we're thinking about the switching film. We're going to engineer the switching film so we have great, easy paths for the vacancies to follow. If we think about the electrode engineering, we need to do this too. And we need to think about what kind of source and sink of vacancies can we have, because we're going to have to move vacancies out of the switching film into the electrode and back again in an easy way. How do we do that? Well, one way to do that is to form a mixed ionic and electronic conductor. So that could be the whole electrode, or it could just be at the interface where the vacancies move in, but you must have it conducting and electrically, and they can move back. So you have vacancies passing all the way across here easily. And the last area is to engineer all of these things together. So I'll give an example in the ferroelectric film where we can control the channels in the electrode, control the channels in the switching layer, and have these highways of oxygen vacancies by these domain things that we're going to have going right across this interface. So we're going to look at just a few examples where I can show you that things can be so much better, properties can be so much better. We can understand what they are by engineering these structures. Now, remember, this traditionally isn't done. People tend to think of a film as just a simple plain film. If you go to structural materials, people definitely think about controlling their microstructures, making composites, making different structures to pin dislocations, or to just change the structure to get the mechanical properties. But you don't think of that in film. So it's translating some of that knowledge really across to the electronics area. So I'll give some examples. And just to say, our modus operandi is to understand the basic science in model systems and then try and translate that to practical systems. So when I say a model system, that might mean a high temperature grown, perfect epitaxial system, so that you just have, you're only looking at the electrode interfaces. So this first case that I'll show you is that we're going to create a perfect vertically aligned nanocomposite where we have channels for the oxygen vacancies to go up and down. But everything else about it is, there's not lots of defects in it. It's really quite high quality material. But from that, we learn what we need to do to then translate that to more basic systems later on. We start at the high level, and then we move down to transitioning to things that are useful on an industrial level. And you can't do it without that whole path, because you do have much learning to do along the way. Okay, so let me give you that example first. And this was some work we did around 10 years ago, and with a wonderful Korean postdoc, in fact, in my group, where we said, let's look at these ionic channels. Let's create ionic channels, and let's create vertical conducting channels in this composite kind of structure here in a thin film. It's highly epitaxial. It's like a single crystal. And let's see, can we, by understanding how the oxygen moves, by making the path straight, by controlling this beautiful structure, can we get much better properties? And so, of course, I'm going to say yes, but this is what the structure looks like on the left here. We have about 20 nanometers pillars, the matrix material, and that's what it looks like on the surface, like pillars in a matrix. It's like a butterfly wing structure, but it's at a much finer scale because the butterfly wing's a micron sort of structure. This is nanometer. And we can look at these lovely epitaxial materials. And so we've got an ionic conductor with an interface that's conducting, formed by mismatch of the structures, with the strontium titanate as the matrix. So it's a complex, quite complex. It's a self-assembled structure. It grows very easily through from one target by pulse laser deposition onto a substrate at high temperatures. It grows and self-assembles easily. That's another story about how we do that. But I want to just show this model system allowed us to understand what's going on. But this was now going to act like synaptic cleft between two synapses. So in the brain, you have the synapses at the ends of the neurons, and you have current pass along that by potential, the action potential, which is a spike voltage, which enables ions to flow across the neurons, across the synapse in this synaptic cleft. So what we're going to do is we want the same thing. We want the voltage across here, and we want the ions to flow across the cleft. And so the top and bottom synapses, that's like the electrodes in a way. If thinking it in a very simplistic way, of course, the brain's very complex and the ions are complex and how that happens and the biochemical processes. But we have to think of things simplistically, first of all, to get things working. So we were able to show that if you look at the resistance versus the number of cycles, so this is switching this thing on and off, the voltage switching up and down, you can see that the high resistance state always stayed the same, no matter what the composition of the ionic conducting electrolyte is. And the low resistance state could be tuned, and that low resistance state is precisely tunable by changing the mobile oxygen vacancy concentration in the ionic conductor. It goes this way, then it goes that way, because as you put lots of vacancies in, they start to coalesce, and so they're less mobile. And this is exactly in line with the conductivity, ionic conductivity. So that was very nice. We could see, you really need to control the vacancy concentration. The switching process occurs by those vacancies changing Schottky barrier height at the electrode. And so that's what you have. And we showed that you could get very nice retention and endurance, number of cycles. We could do this many, many thousands of times and it always stayed the same. Of course, you could do much, much longer times. It was an initial demonstration here a long time ago, but it was uniform and critically, I'm going to just show the points we want to get. We want to get all of these properties together, remember? And the key thing about this was it was not stochastic. We created fine, predefined conducting channels. They weren't random filaments. They were predefined. We understood that's a good way to go. If we can do that in other systems, that will be really good. Of course, the cost of this is quite high. So it's not about actually making a practical device. We're about learning. But we want to obviously get that red arrow away. We want to make it compatible, CMOS compatible, and lower the cost. And that's the journey we're going to go on in the talk. We'll keep going along that journey with a few examples. So now we've gone through this high temperature grown material. We showed that we can get control of the vacancy channels and uniformity. Now we want to say, well, actually, those are high temperature grown. We can reduce the temperature a bit, and we can choose materials which are more simple. So we now want all CMOS compatible materials, which those weren't before. We want binary oxides, and we want to try to lower the temperature a bit. Furthermore, we also want to think about what happens at the when you move the oxygen down, and where does it go? It will be trapped at the interface unless you can move it down into the electrode. So here we want to add in this mixed ionic electronic reservoir layer where we can have the vacancies going in and out and also conducting. So that's what I'm going to show you next as an example. And here what we've done is we've made very fine confined oxygen vacancy channels. And where are they? They're at the boundaries between two materials like we had before. So this is a composite, cerium oxide and tungsten oxide. You say, why those materials? Well, they are CMOS compatible. And the cerium oxide is quite a good ionic conductor as well, especially when it's got some vacancies in it. And you have these interfaces again. They're not as nice as the vertical interfaces. Remember, these are simpler systems now. Temperature's a bit lower. But you still have vacancy channels, as we see on the right here. And furthermore, we have this interface region, which you can't see very well in that image, but we show another image here, much higher magnification image, and we could see that we actually have this thin blue layer above the electrode, and that's all tungsten oxide. What we have here is a tungsten oxide mixed ionic electronic conducting layer, which can act as a reservoir of the channels, the conducting channels. The vacancies come up and down, let's say not quite straight, but up and down the film, and they can have a reservoir to go in and out of at the bottom. So that was interesting. And we had all sorts of measurements, but I'm not showing you, to prove that actually it's not a pure filamentary system, it's a confined filament. And there's many other measurements around this, but just showing you how to engineer these materials, basically. And if we look at the performance of these, we can see that we have high resistance state and low resistance states, the number of cycles, that's 10 to the 6 cycles, and the resistance versus time. This is looking at the retention. Do you retain the states when you take the voltage off? The high resistance states and the low resistance state, take the voltage off, just leave the material, look at the resistance, and you see that you can go quite a good number of cycles. And you can say, well, they're better in the literature if you tune other things and you put other layers in, but actually this is a very simple, it's a one-shot single layer film. And furthermore, it's CMOS compatible materials. And furthermore, we understand what you need to do to improve this tungsten oxide. The tungsten oxide in the literature and then our tungsten oxide, what we've shown is that you need to have the reservoir, you need to have these confined filaments. So we get better retention endurance than other reports. You compare just single layers. So we've showed that the good part about this work, this particular study here, is you get very good endurance for tungsten oxide as an exemplar material by controlling the structure, basically. But let's move on a little bit now. We want to go and think about getting it even more compatible for industry. We want to make columnar grains. So we're going to grow grains of a columnar structured material. And we're going to still have this mixed ionic conductor layer underneath. And what I'm going to show you is that actually this is even better. And so what we have here actually is doped hafnia. It's a very interesting material because industry love it. It's already used in gate dielectrics. And all we've done here is we've tuned it. So it's simple materials, but it's about tuning them. So we've doped it to make it highly resistive. And we've also doped it to create some oxygen vacancies in it. And underneath that, we've created a mixed ionic electronic conducting layer of titanium oxynitride. So you start out with hafnia on top of titanium nitride on silicon. During that growth process, you have a partial oxidation of the titanium nitride. And we find through a lot of operando measurements that the vacancies are moving in the TiON. So you see here, these vacancies move, and then they can, it's like the reservoir here, and then you can move the vacancies up and down the grain boundary channels. That's an interpretation of what's going on. There are other interpretations. There's always, these systems are actually quite complex. You never quite know it then and just get exactly what's going on. But what you do know is that if you get good properties, you can have some future to keep improving and to keep making it more CMOS compatible. That's always our thinking. So here we're going to say, look, here's the synapse. And this is the material that's going to go in between these two synapses, and we spike the voltage just as the brain has the action potential and spikes the voltage, move the ions across the synapse. And we see that with 6,000 spikes of the 1 volt, conductance goes up. That's called potentiation, and it goes down again, depression. And so this is how the brain learns, by changing the weights across the synapse. And you see there's linear regions, which is, of course, what everybody would like in the computer world, because you don't want variability and hard to understand curves. So linear curve. And we could get nice multi-level states. As I said to you, you must have multi-level states so you can, in the crossbar array. And then we looked at the number of levels you can get here. The currents are very low as well. You'd be like 100 nanosiemens. The conductance, the number of levels is around 6,000, which is a record for Hafnia. And we could get large conductance ratios, which means more multi-levels. This is very promising. So the best thing about this was voltage and currents are low, and the many multi-level states. So it's this iterative process of understanding what's going on and improving it. So now I'm going to show you very briefly how we now make this similar system, but we're going to get the temperature right down. So this is what we want to get to, the pièce de résistance. The thing that you really want at the end is low temperature scalable growth. You want a system that could be used in industry, basically. So here we are growing by spatial atomic layer deposition at only 300 degrees C, metallic oxide material on titanium nitride. It's quite conducting, that top layer, so we call it metal M. Actually an oxide, it's really conducting. And then we have very fine grains. So the temperature's low, so we have very fine grains which have a columnar structure. And we then just going to do an anneal. We're going to oxidize this interface a bit, and we're going to move oxygen around. So one of the layers, the titanium nitride, wants to suck out the oxygen. It takes it out of the top, and it leaves it with a lot of vacancies in it. So a lot of vacancies in the top, a lot more oxygen in the bottom, and that allows us to have better switching behavior, because we now have this TiON as we had before. We show from operando XPS and photoluminescence and electron microscopy that the oxygen vacancies really do distribute after annealing, but we have very good switching because of this imbalance of the oxygen. And so what we see here is, I showed you this synaptic-like behavior before. So this is the potentiation and depression with the spiking voltage. And we find really good programmability. We go 50 cycles of different pulse numbers. So we have 20, 300, 500 pulses. In fact, we get to 1,000 pulses and only a voltage of only less than a volt. So it's like a half a volt, and it's just a single layer of material. So you have an electrode, you put an oxide film on, you do a short anneal, and then you have this wonderful behavior. And the reliability is very good. So here we do we have 10 spikes, and we do that 10 times, and then we cycle it 50 times, and you see still nice potentiation and depression. The conductance levels, if you look at the cumulative distribution function, you see good uniformity and very good uniformity between the number of devices. So it's around 1% coefficient of variation, and the cumulative distribution is also very flat. So this is a very simple, low temperature grown, cheap materials, everything you really want. And furthermore, you can grow it on flexible substrates. So this is very promising for wearable electronics. I know you have a very good wearable department here for wearable electronics. So what we need to do is make crossbar arrays of this wonderful material and do some computation with them, do some work and really low power intelligent devices. So I won't go into that, but these two graphs really just show that the properties are good and that the kind of switching is a sort of an intermediate kind of switching. It's not traditional. We've engineered the materials to get a new way of switching. So finally, we get all of these properties together. So it's a story of perfect materials, understanding the engineering, choosing the right materials, learning process, and a gradual process that takes many years, in fact, to some other materials in the end. This is one example. We have others where you can really understand what's going on and really get good performance. So that's just comparing the data with the literature, and it just shows that we have many cycles, good variability, simple growth, low voltage, potentiation depression. I'm going to just end on this one slide to say, can we do the same for ferroelectric memristors as for resistive? I didn't talk about ferroelectrics. There really isn't enough time, but I want to show this structure, the interface highway structure. We have the switching layer. You can get stuff easily across the interface and into the electrode. Because if you have interface of two different materials, there's always some barrier there. It's better if you can control how that goes across. So what we see here is we've taken a ferroelectric, which has got controlled oxygen vacancies in it, yttrium-doped hafnia. And if you look at our film, this is our film in pink is on silicon. Our reference film is on a single crystal. And you'd always expect a single crystal to be better, but it's not, because single crystals, it's going to be uniform and all that. But the silicon is actually better. And the reason is because we've created these channels here by crystal mismatch domain formation. So you grow many layers. It's all the initial layers by sputtering, and then it's pulse laser deposition after that, but it could be sputtering as well. And you see that you create these channels all the way through the film by having domains that just slightly rotate. That is what gives us this very excellent endurance, 10 to the 12 cycles. And as you see over here, comparing the data with the literature, here's the imprint. It's very, very small. That means the vacancies are not getting tracked. And it's the combination of the imprint with the cycles, which is good. So other works, they have, this work is good. It's on single crystal, but it's single crystal, so it's not so useful. And all the other single crystal stuff's down there, and all the other silicons down there. So it's a good result of understanding this interface oxygen transfer. Okay, I think I've said enough. I think I've taken you all through this wonderful world of materials engineering at the nanoscale in thin films. I hope I've convinced you that it's really important not just to grow a film that's just a single film, but to think about how you structure that film to get the performance, especially with oxides, to move the oxygen in the right way. And this was just to say, this is very interesting, but of course it's not CMOS compatible necessarily, but we've learned exactly what we need to do in terms of getting these channels across the boundaries. Okay, so my summary is that oxide electronics has huge possibilities. It's a pretty untapped area today. We're going to hope that AI helps us to understand how to engineer things better. I'm not convinced that's going to happen that soon, because these are subtle things that often are not published or just not quite out there yet. But anyway, materials engineering is central to application success, because you've got to get the performance. And the only way to get the performance in these complex materials is really to nano-engineer them. I've shown that you can control vacancies in thin films in new ways, and it's crucial to control concentrations and transport pathways. I've shown some really good performance in different resistive and ferroelectric switching materials. And I hope that engineered perfect films is going to be a bigger area in the future to create electronic devices for all sorts of other memory and communication and energy areas besides. There's many, many areas that could benefit. Of course, I want to thank my group and all my long-term collaborators. Can't mention everyone, but some of the key people have been on this work here. And of course, my funders. Of course, we can't do anything without our funders, so very grateful to those as well. And I'll leave it there, and thank you for your time. Over there.
Thank you very much, Professor Driscoll. That was a wonderful talk. Can you hear me? Yeah, now the floor is open for question. And anybody, let's go. Professor Yan Feng from Applied Physics.
Okay, thank you. Very nice talk. So you show the effect of this oxygen vacancy on the conductivity of oxide materials. Now you also show the effect on this ferroelectric here, right? What is the correlation between these two materials? Yeah.
Between the resistive switching, the
Resistive switching and ferroelectric.
Yeah, well, the correlation is that they both have oxygen vacancies that move when you apply the field.
Oh.
So the ferroelectric materials, that's a part of the switching mechanism, and the change of the polarization is the vacancy movement. So there's a lot of people working in both areas, but haven't really connected the two, I think, so well. And so the point is, in both systems, you have to control the vacancies, not just in the film, but transport into the electrode and out of that as well. So the electrodes are very important as well.
Okay, thank you. So here you demonstrate the state of memories to be up to several thousand by tuning this oxygen vacancy diffusion, right? And you also show the possibility for synaptic application. And if we consider ferroelectric film, is it possible to show this similar effect?
Yes, it is actually. So I could have talked about that as well. But the ferroelectric, of course, when you polarize the ferroelectric,
yeah,
you polarize it gradually. So obviously you get to the point where you get to the coercive field, and then you form the domains are all aligned, and then you switch it. But before you get to that, you can have the subcoercive field. You can gradually polarize the material. So that's another. You can also see similar synaptic-like behavior by gradually polarizing and depolarizing.
I have the last question. It's about the possibility of this type of technology for practical applications.
Yes.
Conductivity is related to oxygen vacancy, right? How can you control the density of oxygen vacancy is application of thin films? Because is for oxide thin films, we cannot easily control this type of defects.
That's a very good question.
Thank you.
I think what we believe is that you need to not use any old random oxide. If you take, say, TiO2, which is the first material that was looked at in depth, the switching, you don't know what the vacancy concentration is going to be. So I would say what you need to do is to take an oxygen ion conducting material where you make structural vacancies by doping. So in fact, the case of yttrium doped hafnia, which is the ferroelectric, you have yttrium 3+ on hafnium 4 site. You create an oxygen vacancy to compensate for that charge difference. Half an oxygen vacancy, you know what I mean? So it's compensation by forming vacancies when you dope, rather than just random formation. So actually, ionic conductors are very good because you're actually controlling the vacancy concentration. However, you may say, well, they're ionic conductors, so the oxygen's quite mobile. Then some people say, well, the retention's not going to be good because the oxygen's mobile. So when you take the voltage off, you're going to oxygen is going to diffuse away. But it depends what you do and how you do it as to whether that's going to happen. But I think oxygen ion conductors is the way to go.
Okay, thank you.
Yeah.
Thank you. We have quite a few questions online.
Oh, great.
So I need to translate the first one. And you have talked about three methods. One is to control the oxygen contents locally. Second one is to control the nanostructure and the interface engineering. And respectively, what kind of property problems did you solve? And whether you can achieve a synergetic effect.
What kind of property problems did we solve? Yeah. Well, we solved the problem of, so by controlling the vacancies and controlling the structure, we solved the problems of stochasticity. So that's a key issue for resistive switching materials, is the variability between devices and non-uniformity as you go and cycle them. So we solved stochasticity problems. We've improved endurance a lot by having confined filaments and a hybrid kind of switching mechanism, and also having a reservoir. So it's this sort of many things you have to do to actually, because you've got a device that's made up of a film, an interface, and an electrode, and you have to control those three things. If you don't control those three things, when the oxygen's moving across there, you're going to get problems. So we've improved, we've learnt the structural aspects and the compositional aspects that give you much better performance in terms of what are they, endurance and uniformity, and reducing stochasticity, and also doing things at a lower voltage and current as well. So all of those memory requirements that I listed, we've been able to achieve much better performance in those things through this long-term approach, basically.
Thank you. And next question is, what are the key engineering strategies to bridge the gap from excellent functional property to practical device application for oxidized electronic materials?
That's a good question. What are the key
engineering strategies?
Well, of course, the first thing you want to do is to make sure that when you grow your films, your deposition equipment is well controlled. Because even if you do all these wonderful things in controlling the material, and your system for growing the materials is not well controlled, you're still going to have a lot of variability. So that's the first thing, really well controlled equipment. Now, the truth is, in university labs, it's not as well controlled as we'd like, because you're relying on wonderfully hardworking students, of course, to maintain it, but that doesn't always happen. So, but having that is the important thing. So that's the first thing. That's the basic point. You want to know what substrate you've got. Is the surface of your substrate clean? Is the surface of your substrate the same from one growth to another? If you're using silicon, is it full of silicon oxide on the surface? Is it smooth? That's the base. These are the basic things. When you're growing by vacuum depositions, such as we are, sometimes it's not vacuum. Sometimes we're doing this spatial ALD, as I mentioned. But when you're doing that, you've got to make sure your precursor materials are also well controlled. If you're using pulse laser deposition as a sort of a tool to understand what's going on, you've got to make sure that your ceramic targets that you're going to ablate have the right density, that the density of them, that the materials that in those precursors are clean and pure. The surface of the target is not being conditioned in the wrong way. So there's all those really fundamental things about the growth first, in terms of the actual process. Then we get onto the talk that I did. We have to assume that that's all right first, and then we get onto the bit of the materials engineering at the nanoscale. So then you have to go on to that. The problem is, of course, is that if you're trying to get the properties that silicon has, you have to remember silicon's a single crystal. And in the semiconductor fab process, everything's so perfect. So you've got to be able to control the deposition and then control the materials at the nanoscale in the ways that I talked about, basically. Not easy though.
Yeah,
It's not easy. With oxides, it's not easy at all. And I think there's a lot in the community. People don't often want to say that because they want to just keep inventing, making a new discovery. And that's wonderful because there's lots of beautiful physics out there with beautiful papers published. But I think it would be wonderful if we could translate that beautiful physics to real applications. So it does require all these other things to think about, I think.
It's not easy, probably.
Yeah.
Hi, Professor.
Hello.
I think your speech is very impressive, especially the strategy part you just mentioned before. But I have a question. I mean, inside your whole structure, I noticed that there is a trade-off between the data retention and the device endurance. I mean, yeah, I mean, maybe the better vacancies we get, and we may get the liner outcome and the better speed. But at the same time, the vacancies will be very easy to escape and diffuse. But if likewise, it will shorten the lifespan of the whole procedure. So you mentioned the strategies things if we want to promote it, how to balance this kind of trade-off.
Okay. That's a good point. Very good question. Yes, you want to balance, you want to have good retention and good endurance. And as you said, you don't necessarily have those things at the same time. But good endurance is about moving the oxygen a lot, being able to move it easily, right, without it being trapped. And good retention, you will say, well, actually, that means that if you move it easily, then it will diffuse away when you take the voltage off, right? So I know what the question you're asking, but you have to think about ways you still have to have the oxygen that's mobile, but remember that's mobile under a field. When you take the field off, it's not so mobile. Now you say, well, it can still be somewhat mobile, but you can think of strategies to choose materials that it's not so mobile, but it is mobile under a field. So it's thinking about that aspect.
May I ask one more question? But what if we may run into some random noise? I mean, even though we can keep it in the vertical methodology, but we will still run into the random noise, and at the same time, we may run into this kind of trade-off between the retention and this vacancy problem. So yeah, so it means that we will face trouble from the inward and outward. So how to balance it?
So in terms of it depends, of course, on the application. For some of the in-memory stuff, for the neuromorphic stuff, the retention doesn't have to be so long anyway, in fact, but for the inference. So, depends what numbers you want to get, right? So obviously, if you're thinking about some kind of memory where you have to have really high values of retention, then there may be challenges if the oxygen is quite mobile. But for the brain-like computing stuff, you don't have to have retention values that are extremely long. So that's that point. What you want is to have this very good synaptic-like behavior. And the synaptic behavior, I just showed one aspect of it. There's many different types of synaptic behavior that you have to achieve.
The methodology is not always static, to always change due to the target is changed, due to the mobility is changed.
That's right.
Thank you.
Yeah.
Thank you. Can you identify yourself, please? Yeah.
Yeah, I'm just a master student majoring in international management and leadership.
Okay.
Fantastic.
Yeah.
Great.
Thank you. Okay. Do we have any more questions? Yeah, please.
Thank you very much for your very insightful talk.
Just identify yourself.
Okay, I'm a PhD student in a major in applied physics.
Physics.
Yeah. So it is very amazing that you can use the boundary to control the vacancy so well in the channel and also in the interface. But I want to ask a question beyond this crossbar array, because we know that the memory-stir crossbar array is mainly have most applications on the edge computing, like the neuromorphic device. But for the edge computing, the crossbar array to implement the practical use on the edge computing, it needs the referral circuits like the ADCs and DACs and other stuffs. So so what do you think the really actual use of the future of this part?
About the peripheral circuit.
Yeah.
I mean, I think that's a big area, and it's a very important area, and it's a very good point that you have to have the A to D analog to digital conversion and back. And there's a lot going on in that area, but that's not really my expertise, to be honest. So, but it is a very important topic. I'm not 100% expert on that, so I can't really comment on it, but it is a very important area as well.
Okay.
Many different levels, right? There's the materials, the devices, the circuits, the systems, everything. It all has to work. And then you have to have the algorithm part as well.
Okay, so thank you. I have another small question about the channels. Like you mentioned, when you have more cycles in the end, like 6,000 times, then I noticed the data is like degrading. So what can we do to have some solutions to fix that? Like you know, the channel is vertical. So can we have a method like GAA to have another labor field to control the channel?
That sounds a bit complicated. I think really we need to, what we're doing is just trying to demonstrate what you need to do to improve things. And of course, there's always more to do, certainly more work to do. So I think, we could think about making the interface, making things, at the moment you see the structure a little bit rough. So I mean, we could think about how to make that smoother, probably preparing the silicon better in the first place, controlling the oxidation step more carefully, or putting even the conducting channels into the hafnia in different ways, by some iron milling or something like that. So there's many different ways of tuning it to make even further improvements, I would say. But I think, what we're trying to do is just demonstrate what you need to do in terms of the structure to make things work well. There's always more.
Okay, thank you. Thank you so much.
Yeah. One more question online. Emerging applications such as neuromorphic computing, what are the stability and scalability challenges faced by these?
Stability, well, again, that relates to, the cycling, how many times you can cycle it, and how stable the interfaces are, because a lot of things are interface driven. So can you make materials where the interfaces are very stable? So it's about the material selection, and it's about growing things in a highly perfect way. What we do in our lab, in students doing it in a university environment, things are not really highly controlled. You do the proof of concept work. So stability is about materials choice and about how you control the growth, really. And the scalability, how much can you shrink it? That's how can you make it small, and also how can you make it on a large scale? Yeah, I mean, often the problem of oxides is once you try to shrink things down and you process them and you mill them, very fine scales, you can actually induce extra vacancies at the edges and edge effects. So that's something to be thought about. I think if you're thinking about sort of just really simple, basic wearable devices, you may not need to go to very high densities. I don't think we are thinking to put these things in the cloud. We're not thinking about making different sorts of GPUs or whatever. It's about more practical IoT, cheaper throwaway devices or wearables, that kind of area. So, and the scalability is always a challenge, but not as much of a challenge. But there's a lot to be done to understand about that as well. It's a very good question. I can't give you a full answer.
Yeah,
good question.
I finish off all the online questions. Any other question? Actually, we are working on wearables. And
that's wonderful. I'm going to learn from you.
More status, it don't need to be 6,000.
Yeah.
Probably some question we're working on 3 level is good enough.
Yeah.
Or 2 level, even 2 level is okay. So definitely in this area, a lot of scope.
Yeah, no, I'm looking forward to collaborating with you, Professor Chow, now on this.
Yeah.
Learn a lot from you.
Yeah, we can chat
Great.
about
It's
this.
exciting. Yeah.
And any other questions? Yes, Professor Su from Mechanical Engineering.
Yeah, Judith, thank you very much for your very fantastic talk. I'm not precisely in that research field, so allow me to ask you one question which is relevant but not directly related to your work. So that is also approach to my research area. So that is you show us you made some beautiful, perfect film, and also like some membrane or something like that, and also you show some characterization pictures about the fabricated material. So I got one question is, so when you make the film or deposit the film on some substrate, so when you do the characterization, did you encounter any challenge or difficult to do the characterization for these very thin, ultra thin films or membranes? I'm asking you this question is because we are doing some more like some NDT material characterization work. Recently, we were approached by some industry in the semiconductor industry. So they said, so they made some film. They also deposited the film on the substrate, but they do have difficulty in very precisely measure the thickness or get some structure information or the material properties for these films once they deposit on the substrate. So do you have any comments on that? Oh.
Yeah, that's a good question. I think sometimes the structure can be a challenge because they may be that you grow them at low temperature, and they may be sometimes they're low crystalline, they're crystalline but only just. So there's nanocrystalline, and then you mill it. So you do some TM, you mill it, and then when doing the milling process, it converts them to amorphous. We can't be sure that it was always amorphous or it was nanocrystalline. So there's one challenge. If they're very thin, you may be looking more dominated by surface effects when you do a characterization. When you want to look through the bulk of the film, you may be, looking at the surface, and then if it's nearly all surface, you may be absorbing water onto it.
Yeah.
So that might change things. It's hard in a very thin film to probe how crystalline it is if you do X-ray diffraction, say, because if it's polycrystalline, you don't get a large signal. So that can be a challenge. It's in terms of uniformity of thickness. I mean, we don't characterize it that well. We do AFM measurements, atomic force microscopy, and we look over a large area to look at the variation that way. Pretty uniform for the deposition methods we use, actually. But if they're semiconductor industry, I don't know what aspect of it they're looking at, whether it's contacts or gate dielectrics or anyway. Yeah.
Okay.
There's many different characterization tools with each with their own challenges, right?
Yeah.
So.
Okay. Thank you.
Yeah.
Hey, thank you. I think our time is up. We probably round up. Can I ask the audience join me, give Professor a big round of applause for a wonderful talk. Thank you. Can keep talking, yeah. Now we present audience online. The meeting is over. Thank you very much for your attendance and your questions. Bye-bye.